Today, we are taking a massive step back to look at the invisible architecture that literally powers everything we do, computer networking. We're going to explore exactly how our devices communicate, zooming all the way out from those messy local cables in your office, right up to the massive global infrastructure and security protocols that keep all our data moving safely.
I mean, think about it for a second. You send a quick direct message to a friend on the total opposite side of the planet. How does that single piece of data travel across this vast digital highway and just magically arrive on their specific screen in mere milliseconds? It's this incredibly complex, lightning-fast journey, and today we're going to break down exactly how it all happens.
So, here's our roadmap for today. First, we'll map out the digital world. Then, we'll look at the actual shapes of these networks. Third, directing the network traffic. Fourth, addresses and network rules. And finally, securing the digital border. Let's get into it.
Section 1. Mapping the digital world, from rooms to continents. To really grasp the sheer physical scale of all this connectivity, we've got to start with the local area network, or LAN. This connects localized devices, like, say, your smart home or your office building, at incredibly fast speeds, mostly because the geographic distance is super small. But on the flip side, we have the wide area network, the WAN. This links those smaller local networks together across vast distances. We're talking massive infrastructure here, like orbiting satellites and those crazy transoceanic fiber optic cables. In fact, the internet itself, that's literally just the ultimate global WAN.
Moving on to Section 2, the shapes of networks, or how devices actually connect.
Let's zoom in on the physical layout, which network engineers call topology. It helps to think of this exactly like city planning. Now, in a mesh topology, every single device connects directly to every other device. What's super fascinating here is the extreme redundancy it creates. Because there are multiple distinct paths for data to travel, if one node just up and fails, the data seamlessly reroutes itself. No big deal. It's highly fault-tolerant, which makes it the absolute go-to for mission-critical data centers.
But contrasting that heavy redundancy is the classic star topology. Instead of everything connecting to everything else, this one relies on centralized simplicity. Every device connects individually to a single central node, usually a switch. Now, this makes the network super easy to manage and troubleshoot, for sure, but it does introduce a pretty glaring single point of failure. If that central hub goes down, well, your entire local network halts completely. So, with those options, how do engineers actually choose? Well, it's all about trade-offs. We've covered star and mesh, but notice that hybrid topology in the middle. It essentially combines the best of both worlds, offering immense flexibility for large enterprises. Though, yeah, it definitely requires some complex management. Then you have the bus topology. Super cheap, relies on one shared backbone cable, and it's great for temporary setups, but a single break kills the whole network. And finally, the ring topology. This one offers highly predictable circular data paths, but again, a single failure impacts everybody. It's this meticulous balancing act of cost, complexity, and reliability.
All right, Section 3, directing the network traffic from roads to intersections.
We're moving from the structural roads to the digital traffic hops, the actual hardware that physically directs our data. Take the basic hop versus the switch. A hub is, well, essentially dumb. When it receives a message meant for one specific computer, it blindly broadcasts it to every single connected device. It's honestly like shouting a private message in a crowded room. It just causes unnecessary traffic. A switch, however, is smart. It actively reads the hardware MAC address of the destination and cleanly, quietly forwards the message only to that specific target. Much better. Now, while switches are absolutely amazing at handling local traffic, what happens when your data actually needs to leave the building? Enter the router. If a switch is your local traffic cop, the router is the global air traffic controller. Routers connect entirely foreign networks together. They analyze IP addresses and use these incredibly complex routing tables to figure out the absolute most efficient global flight path for your data across the vast, wildly unpredictable internet. Section 4 addresses and network rules, speaking the same language. Okay, so how do these devices actually identify each other on a global scale? Well, an IP address is literally the exact digital equivalent of your mailing address. Just like the post office absolutely needs your street number to deliver a package, every single network device needs a unique numeric identifier to send and receive data. It's that simple. Without an IP address, you simply do not exist on the network. Speaking of addresses, 320 undecillion. That is the number 340 followed by 36 zeros. Let that sink in. For a long time, we relied on a system called IPv4, which gave us roughly 4 billion addresses. But with the total explosion of smart devices over the last decade, we basically ran out. So the networking world upgraded to IPv6's 128-bit format. It gives us those 320 undecillion unique addresses, ensuring we are never, ever going to run out of digital house numbers. But, just having an address isn't quite enough. Devices running completely different operating systems need a universal translation rulebook. That's where the OSI model comes in, breaking communication down into 7 distinct layers. It starts at the very bottom with the physical and data link layers. Those handle the raw cables and local MAC addresses. As we move up the stack, the network and transport layers manage the global routing and error checking. And finally, the session, presentation, and application layers handle the connection, the encryption, and the direct interface with whatever web browser you're using. It's just a brilliant framework that ensures your data passes seamlessly from a raw copper wire to a beautifully rendered web page. And finally, Section 5, securing the digital border, building the virtual wall. When we zoom all the way out to the inherently hostile global internet, it becomes clear our local networks face constant cyber threats. As they say, the firewall works like a gatekeeper at your computer's entry point. Think of it just like a security guard at a gated community who's checking IDs. Firewalls inspect the source, the destination, and the internal content of all incoming data. If a packet doesn't perfectly match their strict security rules, it gets dropped immediately. Boom. It is our crucial first line of defense. But of course, one single guard usually isn't enough, right? Robust security requires deep, overlapping layers. You have packet filtering firewalls analyzing those IP rules. You've got proxy firewalls that actually pretend to be you, completely masking your true identity from the open internet. Then there are VPNs, which create a highly encrypted tunnel for your sensitive remote traffic. And for the really active dynamic threats, intrusion prevention systems, or IPS, are constantly scanning for and automatically blocking malicious behavior in real time. To wrap this explainer up, I want you to take a second to look at the very device you are using right now. In this exact moment, you are actively utilizing a wildly complex, lightning-fast network of specific topologies, smart switches, global routing tables, and vigilant firewalls. So what hidden paths and unseen guards is your data passing through right this very second? The sheer architectural brilliance of the digital world is just staggering when you really zoom out. Keep learning, keep questioning, and I'll catch you next time.